Hello, Assalamualaikum. My name is Harib bin Zulkifli. My metric card number is B0422102260. We are from Group C. This is my groupmate, Muhammad Afiq Aiman bin Jamaluddin, Muhammad Hafiz bin Muhammad Faizal, and Muhammad Akmal Alif bin Mansur. CFD or computational fluid dynamic is a powerful tool used to simulate fluid behavior. In our study, we focus on simulating laminar flow over a flat plate. Laminar flow over a flat plate occurs when fluid moves smoothly in parallel layer with minimal mixing. Using CFD, we simulate the boundary layer development and observe how velocity transition from zero at the surface to the free stream velocity. This simulation highlights key characteristics like velocity profile and shear stress distribution, which are essential for validating theoretical prediction. The body layer is a thin region near a solid surface where viscosity significantly influences fluid flow. Depending on the Reynolds number, the body layer can be laminar, transition, or turbulent. The body layer thickness is a measure of how far viscous effect extends from the surface. It increases when fluid velocity decreases, surface roughness increases, or the free stream velocity rise. Understanding this parameter is crucial for predicting flow behavior near solid surface. In a laminar body layer, fluid motion is smooth and orderly with a parabolic velocity profile. Shear stress in this type of flow is relatively low compared to turbulent flow. This characteristic make laminar flow an ideal starting point for studying viscous effect.
Hello, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Afiq Aiman bin Jamaluddin, and I will continue this slide presentation. When the Reynolds number is below 500,000, flow over a flat plate remains laminar. The velocity profile is parabolic, and the flow near the surface is smooth and orderly. This foundationally understanding helps us analyze more complex flow scenarios. Our objective in this study are: the first one is to study boundary layer thickness and laminar flow over a flat plate. Second, to calculate velocity and thickness using CFD simulation. Next, to gain proficiency in using CFD tools. And the last one is to understand fluid behavior near solid surfaces. CFD is a numerical method that solves fluid flow problems by discretizing governing equations like the Navier-Stokes equation. It serves as an alternative to expensive and time-consuming experiments, complementing theoretical method by providing detailed simulations. The reasons to use CFD are: CFD is widely used because the first one, it is a cost-effective alternative to physical experiments. The next one is it complements both experimental and theoretical approaches. And the third one is it is instrumental in research, design, and education.
In this experiment, we focus on investigating the effect of airflow velocity at 1.5 ms and 2 ms on the velocity profile and boundary layer thickness. I will fast forward to the velocity inlet part. This one is geometry details. The dimension is given. The picture shows vertical length is 1 meter and horizontal length is 0.5 meter. purpose of the velocity inlet. The velocity inlet sets the flow entering the domain at 2 ms, perpendicular to the boundary. This defines the speed and direction of the fluid. It helps fluent calculate flow properties like velocity, pressure, and turbulence across the domain. Configuration details. The magnitude normal to boundary option ensures that the flow enters perpendicular to the inlet surface. The absolute setting indicates that the velocity is defined relative to a stationary coordinate system. The supersonic initial gauge pressure is set to 0 PA, meaning no additional pressure is applied at the inlet beyond the default reference or atmospheric pressure. Pressure velocity coupling. First, scheme is set to simple. The simple scheme couples the pressure and velocity fields to solve the Navier-Stokes equation. It is efficient and stable, making it suitable for steady-state simulation. In both cases, the result shows smooth and stable behavior. For the 2 ms airflow, the black line is higher, meaning it takes more effort to stabilize than the 1.5 ms case. The red line and green lines drop similarly in both but are slightly lower for 2 ms, showing better accuracy. The 2 ms case also converges faster, finishing in about 110 iterations compared to 140 for 1.5 ms. The result show the difference of visual contour for static pressure at airflow 1.5 ms and 2 ms.
Okay, now I am Muhammad Hafiz bin Muhammad Faizal. I will continue the presentation. Okay, in this slide, I will talk about relationship between result and theory. Our CFD simulation validate theoretical predictions. First, velocity plot. The velocity transition from zero at the surface to the free stream value, following a smooth parabolic profile predicted by the Blacher's solution. Second is velocity magnitude. The velocity magnitude profile shows a gradual rise within the boundary layer, aligning with theoretical expectation. Any deviation observed can be attributed to factors like measurement errors or surface roughness. Okay, lastly is our conclusion. In summary, our study used CFD to simulate laminar flow over a flat plate, providing valuable insight into boundary layer development and velocity profile. By comparing results with theoretical prediction, we validate the behavior of fluid flow near solid surface.